All right, cool. So as part of my day job, I lead the database team at Heap. And so in order to do my job effectively, so for my day job, I have to optimize a petabyte scale Postgres cluster. And so in order to do my job effectively, I need to be super familiar with the ins and outs of SQL and all the different kinds of tricks you can do. So I'm going to show you how you can use some of the techniques I'm familiar with to generate fractals with SQL. So just a brief overview of SQL. So in SQL, you operate on list of rows, which you can also call a table. This table represents a list of books. So in a table, you have some set of fields, a title, author, and so for books, every book has a title, author, and cost. And you can see for each book the corresponding values of those fields. And so the most basic operation you perform on a table is a select statement, which is give me these fields from the table. So in this case, we're asking for the title and author from the books table, and we get the title and author of every book. Now, an operation I'm going to be using a ton throughout this presentation because it makes SQL queries a lot more legible is a CTE, which is a way of defining variables in SQL. So in this case, we're defining Dan Brown books to be the result of running the query that gets all books authored by Dan Brown. And then you can use Dan Brown books as if it were an actual table later in the query. So below we select the number of Dan Brown books by using Dan Brown books, which refers to the results of the query from before. So now that we've gone through a few basics of SQL, let's take a look at how we may go about generating a fractal with SQL. So Sierpinski's triangle is a very well-known fractal. And one really interesting way that you can generate Sierpinski's triangle is with bitwise AND, where if you take a grid and you mark all the points where the bitwise AND of the row number and column number is 0, this will give you Sierpinski's triangle, surprisingly. That's what this example here shows. So in order to write a SQL query that does this, we can do this in a 3-step process. First, write a SQL query that produces one row for each cell of the grid, and then go over that and mark all the cells where the bitwise AND is 0, and then concatenate all the strings together to form the final fractal. So now we can generate the cells using this query here. We're using 2 different Postgres features, generate series and cross join. Generate series gives you a list of numbers, so we call it once to get the row numbers and once to get the column numbers. And then cross join takes the results of 2 queries and generates every pair of values between the 2 queries. So in this case, we're using cross join to get every pair of row number and column number, which gives us our grid. Now, for marking the points, we can use this feature case when, which is like if else in any other programming language. And so in this case, we're using when the bitwise AND of the row number and column number is not 0, we mark the point with a space, and otherwise we mark it with 2 asterisks. And you can see below that we have marked all the rows where the bitwise AND is 0 with 2 asterisks. And then we can use this last little query here to combine all the results together. It works in 2 steps. First, by combining all the cells in each row together and using the string ag function, and then it uses string ag again to combine all the rows into a single string, which is our result. And so if you run this query, it's a 13-line SQL query, not too long, you get Sierpinski's triangle. And so the next question you may ask is there any way that we can reuse the same idea to generate other fractals? And so if you take a look at the query we had before, there's this little part here where we use bitwise AND to determine whether or not the point should be part of the fractal. And if you think about it, we can actually replace this with an arbitrary predicate. So if for a given fractal, we have some way of determining whether or not each point should be part of the fractal, we can put that predicate here, and we'll then have a query that will generate the given fractal. So a well-known fractal that has this property is the Mandelbrot set. So you can test whether or not a point is part of the Mandelbrot set by repeatedly running this formula. And if this formula does not diverge to infinity, the point is part of the Mandelbrot set. So in order to express this definition in SQL, we need some way to express iteration, which you can do with this Postgres feature known as recursive CTEs. So for recursive CTE, you specify an initial query and a recursive query. Postgres will first run the initial query and then take the results of that and feed that into the recursive query. It'll then take the results of the recursive query and feed that back into the recursive query and keep doing that until the results of the recursive query returns no results. So as an example, we can use this to generate the numbers 1 through 5. So our initial query is select 1, which gives us the row 1. And then the recursive query is select I plus 1 as long as I is less than 5. So you take the result from the initial query 1 and feed that to a recursive query, get 2, and then 3, and then 4, and then 5. And then since 5 isn't less than 5, the query returns no results, and you get the numbers 1 through 5. So we can use this idea to test whether or not a point is part of the Mandelbrot set. We repeatedly run that formula from before 1,000 times, and then check whether or not the point diverges or not. So we can then modify our query from before, but we replace the condition of bitwise AND with testing for each point whether or not it diverges to infinity. And so if you now run this query, you get the Mandelbrot set. So now the really neat thing here is that there's actually a whole bunch of different fractals that use the same general approach, known as escape time fractals, which are all based on running a recurrence or formula over each point and using that to determine what value, like whether or not the point is part of the fractal. So one example is this fractal from the Julia set. It looks something like this. Uses a very similar formula to what we just used. We change our SQL query like this, and we get the fractal. So there are a whole bunch of different fractals that you can generate using the same approach. I don't have time to go through them. But so this one relatively simple SQL query can actually generate a whole bunch of different fractals. So in addition to the escape time fractals, there's a whole bunch of other kinds of fractals too. So let's see if we can generate another class of fractals. One interesting class are self-similar fractals, which are described by taking an initial pattern and repeatedly applying some rule to it to generate the next version of the pattern. So in this case, we have the Hilbert curve, which is a path that initially starts in the bottom left, goes to the top left, top right, and then bottom right. And you generate the next iteration of the Hilbert curve by replacing each of the vertices with a U-shaped curve. So for the second iteration, it still goes from the bottom left to top right to bottom right, but you now have a U in where all the vertices were before. And you repeatedly do this, and it gives you the next iteration of the Hilbert curve. So in order to generate this with SQL, we need some way that we can represent this. And there's actually a really interesting way that you can represent self-similar fractals known as Lsystems, which are a way of describing a self-similar fractal as a string. So you start with an initial string that describes the initial iteration of the fractal, and you have some rule for modifying that string to produce the next iteration of the fractal. In this case, for a Hilbert curve, the initial string is A, and to generate the next iteration, you replace all the occurrences of the character A with the corresponding string, and you replace all the occurrences of B with the corresponding string. So if you run it through the first few times, you get this sequence of strings. And then this string actually describes a path that produces the Hilbert curve, where if you interpret all the F's as moving forward, all the pluses as moving right, and all the minuses as turning to the left, this path will give you the path of the Hilbert curve. So now, really crazy idea. Let's try to write a SQL query that processes Lsystems. So if we were able to write such a SQL query, we'd be able to feed in any Lsystem we want and get the corresponding fractal. So in order to do this, we could do this in a two-step process. First, write a SQL query that runs the Lsystem, and then a second query that converts the Lsystem string into the fractal. So writing a query to run the Lsystem is surprisingly straightforward. We use a recursive CTE where the initial query is the iteration 0 of the Lsystem. And then for the recursive query, we run the string replacement. So in this case, we're able to use this Postgres function replace to replace all the A's with the corresponding characters and all the B's with the corresponding characters. And so as you can see, this generates the iterations of the Lsystem. Now, converting the string into the fractal is a lot more difficult. We can do this with a three-step process. First, by converting the string into a set of line segments by following the path. Then converting the line segments into marked points. And then concatenate all those points together, similar as to what we did before. So here's a CTE that calculates the line segments. I don't have time to go through it. But the rough idea is that it uses a recursive CTE to iterate through the string. It maintains a current line segment and current direction. And based on what character it is, it will update what character it sees, it will update the state. So if it sees an F, it will take a step in the current direction and emit a new line segment. If it sees a plus or minus, it will change the current direction to turn to the left or to the right. And then for marking the points, we can use this query here. It works by checking whether the point is an endpoint of some line segment? If so, it marks it with a star. If the point is a midpoint of some line segment, it marks it with a bar or dash based on whether it's a horizontal or vertical line segment. Otherwise, it marks it with a space because it's not part of the fractal. And we can use the same query from before to concatenate all this together and form the final fractal. So this is what the full query looks like. It's a 50-line SQL query. So depending on how you think about it, that's either a very large SQL query or a very small program. And when you run it, you get the Hilbert curve. Now, as I mentioned before, we can not only get the Hilbert curve, but we can feed in any L system we want and get the corresponding fractal. So the dragon curve is a very well-known self-similar fractal. If you've read Jurassic Park, it is in all the section title or beginning of the sections. And we can just change the replacement rules, and we get the fractal. And then same thing, here's another fractal board. And again, it has its own L system, which we can just plug in and produce the corresponding fractal of SQL. So using just a few simple SQL tricks, we're able to write queries that can just change slightly and produce tons of different fractals.